Hello everyone, my name is Arya Devdar and this is part 3 of NCERT Class 10 Science Chapter 9 Light, Reflection and Refraction. Okay, so in the last part we saw the image formation by concave mirror, right? And we saw its uses. So there were 6 cases if you remember, and we kept bringing the object closer to the mirror, right? So in the first case it was at infinity, then beyond C, then object at C, and between C and F, then at F, and then lastly between F and P. So the last case was a bit unusual, or the out of the box one, because the image formed was virtual and erect. In all the other cases, the image formed as real and inverted, right? And also we saw the uses of concave mirrors. Now in this part, we'll start with the image formation. We'll start with the image formation by convex mirror, right? Image formation by convex mirror, and we'll see the uses of convex mirror. So there are only 2 cases in convex mirror, not many. I'll tell you the reason as well, right? Next, second, we'll study the sign convention for spherical mirrors. For spherical mirrors, right? So what is the sign convention? So we'll be entering the numerical part, sort of, you can say. Sign convention for spherical mirrors. And lastly, we'll see the mirror formula as well as magnification. So mirror formula and magnification. So what is magnification and what is its formula as well? Okay, so let's start with the image formation by convex mirror. So if you remember that convex mirror is the mirror which is bulged outwards, or it is curved outwards, right? So that is a convex mirror. So there are only 2 cases. The first case is obviously object is at infinity, right? So here the object, this is the object, this is the object, it is placed at infinity, right? And we know that the rays coming from infinity are always parallel to the principal axis, or parallel to each other, okay? So here the rays, 2 rays I have drawn, they are coming like this, and they get diverged, or they get reflected back, and both of them, the reflected rays, they can be traced back to the focus. Similarly for this one, right? So hence we know that the image has been formed at the focus, okay? So position of the image we'll write at F, and it is formed behind the mirror, right? The size of the image, as you can see, it is point sized or highly diminished, right? Size is highly diminished or point size, whichever. And the nature, it is virtual and erect. So you can understand one thing, that in convex mirror, the image formed will always be virtual and erect. It will never be real and inverted. And for concave mirror, the image formed will mostly be real and inverted, except that last case where the object is kept between pole and focus. At that time, the image will be virtual and erect. Okay, so the first case is done. Now moving on to the second case, where the object is between infinity and pole. So here we can't really keep the object between focus and center of curvature, or beyond C, or between F and P, right? Because the focus and the center of curvature are behind the mirror in the case of convex mirror, right? So hence the second case will only remain that the object is between infinity and P. So here the object is kept at this position, and the first ray is thrown parallel to the principal axis. It gets diverged from the focus, right? And the second ray, it is thrown at the center of curvature. And we have studied in the third rule for ray diagrams that when it is directed towards the center of curvature, the ray will retrace its path back, right? So you can see that the 2 rays, the reflected rays, they will never meet in real life. So they have to be traced back, and when they are traced back, they intersect at a particular point, and that is the point where the image is formed, right? Okay, so the position of the image, as you can see, it is between the pole and focus, right? So it is between P and F. The size, as you can see, it is diminished. It's not very small, but it is still smaller than the size of the object. So the size is diminished. Okay, and the nature, it is virtual and erect, as I said. In both cases, we get virtual and erect. Okay, understood? So these are the 2 cases for convex mirror, the image formation. Now moving on to the uses of convex mirrors, where convex mirrors are used basically. Okay, so the first use of convex mirrors is as rear view mirrors in vehicles. Rear view mirrors in vehicles, right? So why it is used as rear view mirrors? Because uh, the convex mirrors, they give a wider field of view. Okay, the convex mirrors, they give a wider field of view, and the image formed is erect, right? It is erect and it is diminished, although it is diminished, but still it is erect, right? And it's not inverted, because it will be very difficult to figure out how much traffic is there behind us and all that stuff, right? So hence, as it is erect, it is a virtual and erect image it forms, and it has a wider field of view, right? So you can see the whole road behind you, even if you're traveling in a particular lane, right? So that is the reason it is used as rear view mirrors in vehicles. Okay, the similar type of um, like usage, or you can say application, is for security mirrors in ATMs or banks. Okay, I'm sorry, security mirrors in ATMs. So again, it has a wider field of view, right? So you can see the person standing behind you, whether he's looking at your passcode or like that, right? So hence they are called security mirrors. Okay, they are also used as parking lot mirrors, right? So if there is a sharp turn in a parking lot, so then a convex mirror is put there, so that the person coming from one side can see, like, is there a person coming from that side, then I'll slow down the vehicle, right? That is the use of convex mirrors. And yeah, so these many are there. So the third one is parking lot mirrors. Parking lot mirrors. Okay, understood? Yeah. Now we'll move on to sign convention. Okay, so sign convention. Now, the new sign convention, it is known as, for spherical mirrors, it is known as the new Cartesian sign convention. Okay, new Cartesian sign convention. Okay, so what I'll do is I'll draw a concave mirror. Well, like, usually standard concave mirror is used to draw, right? And I'll draw the x and y axis. Okay, like this. So this is the y-axis and this is the x-axis. Okay, and suppose that the pole of the mirror is kept at the origin. The pole of the mirror is kept at the origin. So we know that this is the positive x-axis, this is the negative x-axis, positive y-axis, negative y-axis, right? Okay, now this is the mirror, concave mirror. The same thing is for convex mirror. There's not much of a difference here. Okay, so the first rule, right? There's a total 5 rules are there. Let's start with the first rule. The first rule is that the object is always placed to the left of the mirror. So that means the object will always be placed on the left side of the mirror. That means that the light from the object, right, it falls on the mirror from the left hand side. So like this, the light will fall on the mirror from the left hand side. Always, always. It will never change. Okay, you cannot keep the object on this side just like for fun, right? It's not possible. It will always be on the left hand side. That's the first rule. The second rule is that all distances which are parallel to the principal axis, they are measured from the pole of the mirror. Okay, all distances. Now, which are these distances? So we'll see. The first one we have already seen is the focal length, right? So, for example, if say this is your focus and this is your center of curvature, then the focal length will be measured from the pole. So, pole to focus, that's the way it will be measured. So, that means that the focal length for concave mirror is negative. Okay, I'll write it down here. Concave mirror, focal length is negative, always, always. Okay, the radius of curvature is obviously also negative, but that is not required. Okay, anyways, now two new terms we'll learn. The first one is u, or object distance. Object distance is basically the distance of the object from the pole. So this green part, it is known as u, or the object distance. Okay, so I'll write it here. Object distance is u. It is denoted by uk. You cannot denote it by x, y, z, nothing. U, only u. Okay, and suppose the image is formed. So this is getting a bit crowded. I'll just rub this off here. Okay, so suppose the image is formed here. Okay, so then this distance, yellow one, it is known as v, image distance. Of the distance of the image from the pole, it is known as v, or the image distance. Okay, so object distance is u, image distance is v. Understood? Okay, I'll draw this here. So this is u and v. Understood? So these are the four main distances which we have to, which we have to measure, right? So, okay. And if you can remember, for convex mirror, now we saw for concave mirror the focal length is negative. Now for convex mirror, I'll draw another diagram. Wait. Yeah. Suppose this is your convex mirror. And these are your axes, right? Convex mirror. Okay. So you know that the focus and the center of curvature are behind the mirror, right? So what does that imply? It implies that the focal length is positive. So for a convex mirror, focal length is positive always. Remember this. For concave mirror, focal length is negative. For convex mirror, focal length is positive. Okay, remember it in this way, right? If you keep the origin at the pole, then where is the focus? Is it on the right side? If it is on the right side, the focal length is positive. If it is on the left side, the focal length is negative. Simple. Okay. Here also the object it will be kept on this side. So the object, or u, it will be negative, right? And v is always formed, like not v, image is always formed on this side, right? So it will be positive. V will always be positive, right? For concave mirror, u will always be negative, and v can be negative or positive, because in the last case the virtual image is formed, right? So that means v will be positive, but in all other cases v will be negative. So that you have to understand. Okay. Okay. So we saw the first two rules, right? Now we'll see the third rule. The third rule I kind of explained already. It states that all of the distances measured to the right of the origin along positive x-axis are taken as positive, while those measured to the left of the x-axis are known as negative distances. Okay? They are taken as negative. So this side positive, this side negative, as per the axis. Okay? Also, the distances above the x-axis. The distances above the x-axis are taken as positive. The distances below the x-axis are taken as negative. Again, following the y-axis. Okay? So what this means to say that in the further formulas which we are about to see, we'll need the object height or the image height, both. So in such cases, if the object height is always positive, because it is always above the x-axis, it is always kept on the x-axis, above the x-axis, right? So it is always positive. But image height for concave mirror, it may be negative or positive, right? And for convex mirror, it is always positive. But you don't remember all of this, you don't by heart it, you just understand that the heights above the x-axis are positive, the heights below the x-axis are negative. Simple enough, right? So that those are the fourth and fifth laws. ठीक है, not much difference. The fourth and fifth laws. Distance is measured perpendicular to and above the principal axis are taken as positive. Distance is measured perpendicular to and below the principal axis are taken as negative here. ठीक है, understood. So these are the these are the 5 rules for sign convention. So I hope you understood sign convention. Now we'll move on to the formulae part. Okay, now we'll move on to the formulae part. So the first formula we are going to see, and it is very important, it is known as mirror formula. Okay. So as I said, in this formula we are going to require U, we are going to require V, and we are going to require F. So quick recap, U is object distance, V is image distance, and F is focal length. Am I right? F is focal length. Okay, so now then this mirror formula, it is a relationship between these 3 quantities. Okay, and the mirror formula is, drum roll, it is 1 by V plus 1 by U is equal to 1 by F. Okay, so this is the mirror formula, by heart it. So the proof for the mirror formula is not there in 10th standard, it will be there in your higher classes. Okay, so for now just understand and remember the formula. 1 by V plus 1 by U is equal to 1 by F. And this formula, like in this formula, you have to apply the sign convention. In this formula, you have to apply the sign convention. Okay, so when you substitute the value of V or U or F, you have to use sign convention. So it is using sign convention. ऐसे ही कुछ भी पॉजिटिव नेगेटिव डाल दिया नहीं चलता है. Okay, you have to use the proper sign convention. For example, I'll give you an example. Okay, for concave mirror, we know that the focal length is negative. So for example, if the focal length is given 10 centimeter for concave mirror, then here you will put 1 by minus 10 for concave mirror, 1 by minus 10, so which is minus 1 by 10. Okay, for convex mirror it is positive, so it is, if it is 10 centimeter or 5 centimeter for a convex mirror, it will be written as 1 by 5, nothing else, 1 by 5. Understood? So this was one example. We'll see problems later, but for now just understand this much. So this is the mirror formula. Okay, it is valid for all situations of spherical mirrors, for all positions of the object, no exceptions, Okay, understood? Okay, now we'll move on to the last part, which is magnification. Now what exactly is magnification? Magnification is basically object से image कितना बड़ा है, that is magnification in simple layman language. So how much is the image size greater or smaller than the object size? That is basically magnification. But you cannot write this layman language in your exam, right? You have to use the scientific terms. So then what will you write? So magnification produced by a spherical mirror, gives the relative extent to which the image of an object is magnified with respect to object size. Of an object is magnified with respect to object size. Okay, so I gave this definition very big because it's important for the boards, right? They may ask, define magnification. Okay, it is represented by the letter M, right? Now the formula for magnification is C. M is equal to height of image divided by height of object, right? So if I denote height of image by hi and height of object by ho, then m will be equal to hi divided by ho. Now in your textbook it is given h dash divided by h. You can use whichever is comfortable for you. Okay. Also, m can also be written related to the object distance and the image distance. So related to v and u. So how? M is equal to minus v divided by u. Minus v divided by u. This is very, very, very important. Okay. I'll box it in blue. Okay, you have to remember this. M is equal to hi upon h naught is equal to minus v upon u. Okay. Now, the height of the object is usually positive. Not usually, always. Height of object is always positive. The height of image should be taken positive for virtual images and should be taken negative for real images. ठीक है? So real के लिए hi will be negative. Virtual hi positive. ठीक है? And just remember that if m has a positive sign, that denotes that the image is virtual. And if m has a negative sign, that denotes the image is real. Okay, understood? Also, one more thing. If m is less than 1, that means image is diminished. Right? If m is greater than 1, magnified. And if m is equal to 1, same size. Okay, this is kind of obvious, but I still gave it. Okay. So that's it for this video. We studied magnification, we studied the image formation by convex mirror and its uses, and we also studied the mirror formula. Okay, so that's it for this part. Thank you so much.